Check it out now, y'all.
NanoHub U, online instruction.
Welcome to tutorial 1.4, week 1. In the last tutorial, we talked about how to apply this general set of equations, that we obtained in this week for these various thermoelectric coefficients, how to apply that to a one-level device. And the whole idea was to see something elementary like a one-level device, how you can understand it. And that's something where you can get the correct answers quite easily without getting into the mathematical framework, in a much more elementary way. Now, in this tutorial or this homework, what we want to talk about is a more practical example that you often run into. Namely, consider a typical semiconductor where you have a certain conductance function, you see, which, as you know, as we have discussed, conductance can be written as Q squared over H, that's the quantum of conductance, times this number of modes times the mean free path. And if you want a degeneracy factor, you could throw that in. So usually this conductance function would look something like this. And this would have some variation with energy. We could write it as something that looks like, say, e to the power n, some variation like so. And then there's a chemical potential, which you could vary depending on how what is the equilibrium electron density in your semiconductor. And the question you could ask is, or what this homework problem asks you is, how does the Seebeck coefficient change as the chemical potential is varied? And the basic answer, let me just give you the answer before we get started working on it. It looks something like this. This is the Seebeck coefficient. This is the chemical potential, the location of the chemical potential relative to the bottom of the band. So this bottom of the band is what I'll call the zero of energy. So everything's measured from there. Now, if mu is negative, then the Seebeck coefficient, you'll see, increases linearly. On the other hand, on this side, it gets smaller and dies out. And what we want to talk about is what the slope of this is, why it varies linearly, trying to understand this part. And technically, one point I should make is that when this chemical potential is significantly below the bottom of the band, I think I mentioned that in one of the earlier weeks, that's when we usually call it a non-degenerate conductor. Whereas once it's into the band, that means this part of it is what you would call degenerate. So those are just technical terms. This word degenerate is used in many senses in this field. And so it's important not to get confused by the different uses of that same word. But right now, you see, what we are going to use is this, we'll focus on what's usually called this non-degenerate region in this part. And in this context, what it simply means is that Fermi function, you see, is usually written as 1 over exponential E minus mu over kT plus 1. And non-degenerate simply means that all the relevant energies are significantly higher than mu, so that at those energies, E minus mu over kT is a fairly big number. Let's say 4, 5, 10, 40. So what that means is this is a big number, like exponential of 10 or exponential of 100. And so we don't really need the 1. So you can leave out the 1. So we can write F as just exponential minus E minus mu over kT. And sometimes people call this the Boltzmann approximation. So that's what non-degenerate implies in this context. So what we'll do is we'll be evaluating these coefficients. Actually, we'll just do G and GS because we want the Seebeck coefficient, and that's the ratio of those two. So what we'll do is evaluate those two things, but assuming that when you write the Fermi function, we can write it, we don't need to use the full Fermi function, we can use just this Boltzmann approximation. And that actually allows you to do this integral, see, in a relatively elementary way, relatively simple way. Whereas if you want to use the full Fermi function, the integral is a little more complicated. It involves these Fermi-Dirac integrals, which I didn't quite want to get into. But what we'll do is assume it looks just like an exponential, just like this, and thereby we'll try to get an expression for the Seebeck coefficient in this regime. Okay? So here then, we could say, let's focus on, we're just talking about G and GS. So let's try to get the conductance first. So it is integral dE let me take this off, times derivative of the Fermi function with respect to energy, which is exponential minus E minus mu over kT. As you know, it's very easy to take derivative of an exponential. It's just this, and then you have to multiply by whatever is multiplying the energy. So that's this kT. So that's this 1 over kT. So this is minus dF dE, that quantity. Now we need some approximation for this conductance. And this is where, let's assume, I guess what your homework problem says is, assume that it's given by, changes with E as e to the power some quantity n. You see, this is a proportional to, number of modes and the mean free path. So depending on the material at hand, you could have the number of modes change as e to the power half or as linearly with E. Similarly, mean free path could be energy dependent. And we are saying, well, let's just do a general case where this whole thing is e to the power n. So we'll write G of E as quantum of conductance. That's, yes, dimensionally that's like conductance. And then E over some E0 to the power n. So this is like a dimensionless thing to the power n. So this is what I asked you to use. And that way you have a general answer that applies no matter what n you use. Okay? Now if you use that, then what we can do is rewrite this thing a little bit. We can bring the e to q square over h out front. We could take the exponential mu over kT out front. And then inside you have dE over kT, exponential minus E over kT. And all this, of course, gets integrated from 0 to infinity. That's where it's from 0 upwards. And then you have the E over E0 to the power n. Now this is where it's a little convenient to just change variables. That is, call this E over kT, give it a name, call it x. So that the integral, of course, goes from 0 to infinity for E. For x also it would go from 0 to infinity. So instead of this, let me write x. Instead of that, let me write x. And this one also I could kind of make it look the same. I could put a kT here and then write it as kT, multiply by kT over E0 to the power n. So I've done nothing. I put a kT there and a kT there. But then this thing is independent of energy. I can pull it out. And that way I'll just have an integral over x. So finally what would happen is I'd get q square over h e to the power mu over kT. Then this new factor I can pull out, kT over E0 to the power n. So I got that out. That's out. And then inside then I have an integral that looks like dx e to the power minus x and then x to the power n. That's it. And this is actually a standard integral, which I won't go through because you can look it up anywhere, how that does. And what it gives you when you do that integral is actually factorial n. So if, for example, n happened to be 1, answer would be 1. If it was 2, it will be 2. If it is 3, it would be factorial 3, which would be 6. If it's 4, it will be like factorial 4. That will be like 24, and so on. So that's a standard integral. And so instead of this, I could write integral just factorial n. So this is then our expression for g. So let me write it here. I guess I got to do this right here. Okay. Now what we want to do next is GS. Because if we have GS, then we can find the Seebeck coefficient. It's the ratio of the two. So when doing GS, what happens is, now I put an S here. So GS means I have to add this factor into the integral. So I have to put E minus mu over qt into the integral. Okay. So now when I try to rearrange things, what we'll get is, suppose I could, let me write it on top. So again, let's pull out all the common stuff. So there'll be we can pull out a kt over E0 to the power n like before, and then you'll have a q squared over h, and a e to the power mu over kt. So all the usual things will be out. And then inside, you'll have a dE over kt. So I've pulled this out, done that. Then you'd have the e over kt to the power n. And then you have the exponential. But I now have this additional thing here, which also I could take the q from here, put a k, and multiply with k over q. So this k over q is something I can pull out from the whole thing. So I can write it up front here. Write it with a black pen, so that's out there. And then I have this e minus mu over kt. So I could write that here. So this is the integral that I need to do for evaluating g sub s. Now the thing you'll notice is, now the integral here looks like integral dx e to the power minus x, x to the power n, but then this quantity looks like x minus mu over kt. So I kind of got these two separate integrals. One is the first term, which is like x to the power n plus 1. So when I integrate it, I get factorial n plus 1. That's the first one. And then there's the second one, where it is minus mu over kt, which is a constant, and times the same integral, but with x to the power n. So that's like a n factorial. So that's it, you see. So when I do this integral, then instead of this whole big thing here, I've done this integral, and what I'll get is factorial n plus 1 minus mu over kt times factorial n. Okay, so I have an expression for conductance and I have an expression for GS. And we want the Seebeck coefficient, which magnitude is GS over G. That's the magnitude of the Seebeck coefficient. So when you look at that, you can see some of these terms are common. So all of this just drops out. That's in the conductance and that's also in the GS. So that just drops out. Extra is the K over Q. That's out front. And then you have a factorial n here, but here you have factorial n plus 1 minus that. So you'll get two terms. One is n plus 1 factorial divided by n factorial minus mu over kt. That's it. And of course, factorial n plus 1 divided by factorial n is just n plus 1, because factorial n plus 1 means you start from n plus 1 and then multiply every integer down. And factorial n means you start at n and multiply every integer down. So when you divide them, you're just left with n plus 1. So I can take this guy out and just write n plus 1. So this is the end result, basically. This is what I'd asked you to prove here. The Seebeck coefficient changes linearly with mu. That is, if you remember, I started by saying that if you plot Seebeck coefficient as a function of mu, and we are talking about the non-degenerate side, which means the picture I had, if you remember, there's the energy, this was the E equals 0, and then we had a mu down here. And as the mu goes negative, further and further negative, this thing keeps increasing, because there's the magnitude of the Seebeck coefficient, there's a mu over kt. And when mu is 0, that's when it goes to this value, and that value depends on exactly what that integer n is. But regardless of what the integer n might be, the variation of s with mu then is linear, like so. And this is something that has been observed and experimentally and widely believed to be true. And one of the things this tells you also is the point I had made earlier, that what's the maximum Seebeck coefficient you can get? Well, if you just looked at this, it looks like, well, what you really need to do is put mu many, many kts away. Because if you look at the magnitude of this thing, k over q, I think in one of the lectures I estimated that quantity, it was about 100 microvolts per Kelvin. And so, if mu was, say, 10 kt below the bottom of the band, then the Seebeck coefficient could easily be 1 millivolt per Kelvin. Sure, but why don't we do that? Why don't we use that? Well, that's because, you see, if it is indeed that big, it won't conduct very well, because conductance itself would go down significantly, because, you know, if you looked at the expression for conductance, there's an exponential mu over kt there. And if this is a big negative number, you don't have much conductance left. So overall, it would be like, yes, this might act like a voltage source, but with an extremely high resistance. And as electrical engineers would put it, yes, you got a voltage source, but then you can't draw any current from it almost. So you really cannot use it out here ordinarily. You'd like to have mu be a couple of kt or so, which is why with the best semiconductors, what you usually see is a Seebeck coefficient of on this order, k over q, where mu is just 1 kt, or maybe twice this, or thrice this, somewhere around there. That's what you would typically get. And of course, metals are usually very bad for thermoelectrics, because metals means the mu is positive, somewhere way up here. So you're really talking down here, somewhere way down here. You don't get much of a Seebeck coefficient really. And that's why, yeah, for practical applications, one always focuses on semiconductors, you know, p-type or n-type. Of course, the theory for this part, that would be, in principle, would start from the same equations, but the details would be different because I cannot use the Boltzmann approximation anymore. Because once your mu is inside here, that's when I really have to use the actual Fermi function, which means when we do those integrals, we'll have to use the Fermi-Dirac integrals, which gets algebraically a little more messy, and this kind of beyond the scope of what we want to get into in this course.